Hello guys, in this part we'll be taking a look at implementing our design. Here I have an empty project here in IIC. First thing I'm going to do is add my files. Here I've added the files I've downloaded into my project folder. I'm going to add these into my project. However, it is very important that you do not add data V. You have to put data V into the same directory as blram.v, but do not add this into your project. So I would recommend that you put all of these inside your project file and do not add data V into your project. So I'm going to add these. So here, as you can see, I have my files, and then here in your automatic includes, you will see data V. So let's take a look at our design. So first of all, we have our ports. In the last part, we've talked about these ports. You know clock and reset by now. Data from RAM for the incoming data from the RAM, the write enabled signal, address to RAM, data to RAM for writing to the RAM, and then P counter is your PC or your program counter. And here we have provided you with internal signals. You may, if you need to, add more internal signals, but you should be able to do them with all of these. Here we have our always at pause edge clock, and then at star block. Here we have written some of the code for you. We want you to fill in this part. So here we have implemented BZJI and the add instructions. So we want you to add the BZJ and add-I instructions. So here, let's talk about what each state does real quickly. So this state will read the instruction from the from your RAM. So what does that mean? So if we were to say add 1015, the actual hex number that represents add 1015 will be read in this state. And then in the number one state, here you see that we have received data. So we entered the address here, and then we received it here. So as you can see, in the previous state, we said address is equal to P counter. So if your P counter was 0, you would write 0 into your address, and then in the next clock cycle, you would receive the instruction here. So here, the data from RAM right now is your instruction. What we're doing is partitioning it into correct components. So our opcode is represented by 31st to 28th bits. So if you remember, in the last part we had a figure showing all of these. So from 31st bit to 28th bit is your opcode. By the way, this opcode here includes your I bit as well. So that's why it is 4 bits, not 3 bits. Next, we have our operand 1. Operand 1 represents A. So this is from 27th bit to 14th bit. It is a 14-bit signal. You will write it into operand 1. And the same thing for B operand 2 here from 13 to 0. And then what we do here is write this, which is operand 1, into the address. Why? because in our instructions, in all of our instructions, we need to read A before doing anything else. And then we get into specific instructions. So here for BZJI, we went to state 5. For add, we went to state 2. And for BZJ and add-I, you will do something here. So let's follow add here. Let's go into the second state. So in the second state, we will receive the value inside A and then write the address of B into the address port. So if you remember, here we wrote the address of A into the address variable. So now one clock cycle has passed and we're going to receive the value of A. So you can see that here. Number 1 next is equal to data from RAM. This data from RAM is the address we requested in the previous cycle. So our number 1 is set now, and for add we're going to need the number B, the value inside B. So what we're doing is writing operand 2 into address. And then since we don't want to write anything, we are disabling write enable. And you can keep data to RAM 0 since it's not going to write. So next up, we're going to the third state. In the third state, we're going to receive the value B. So the value of B will be inside data from RAM. So we're going to write that in none2. And then since we don't need to do anything else, we can do our calculation, which is addition, and write it back into the RAM. So for that, we do a check here. If our opcode is 0, which is add, if you want to do add, we use the number 1 we got in the second state and data from RAM to obtain our result, which we write into data to RAM. And then where are we going to write this? We are going to write this into the location of A. So we set the address to operand 1, which is A. Now it is very important to do the distinction between the operand and the number. The operand variable represents A, as in the instruction that you will see there. So if it says add 10, 15, my operand is 10, not the value inside 10. The value inside 10 is stored in number 1. And once we've done this, all of this, our add instruction is complete. So what we're going to do is we're going to increment the P counter by 1. So we're done with this add instruction and we're going to the next instruction now. So we have to increase our PC. Once we have done this, we can go back to state 0. So you have traced the add instruction. Now let's take a look at BZJI. So as was said before, we've come back to the 0 state, and then in 0 state we read the instruction. And then if we encounter a BZJI instruction, let us see what happens. So first off, all of this part is going to be the same. You are going to read your instruction and then parse it. You're going to put the parts into the relevant variables. And then if your opcode is equal to this, it means you're doing a BZJI instruction. So you're going to go to the 5th state. So let's look at the 5th state. So if you remember, In BZJI, we do a single jump. We do not do a check. So we should be able to do this in a single state. So in the previous state, what we did was write the address of A into the address variable. So in this state, we received the value of A inside data from RAM. So what did we need to do in BZJI? We need to get the value of A and then add B into it and then jump to that location. So I have the value of A and then the B value, not the value inside B, but just B, is stored in operand 2. So I add them up and then write this into pcount, our PC. And then rest of it is standard stuff. You keep write enable 0, you don't write anything else, and then you turn back to state 0. And based on these, you're going to add BZJ and add I. So as we said, you're going to add these, and if you want, you can edit the existing states, for example, state 2. And then if you need it, you can write another state as well. So now that we've looked at the structure of your lab, I'm going to complete this assignment and then show you the simulation. Alright, now I've completed my assignment. Now let's go and simulate this. Once again, make sure that your automatic includes have data V here. So let's go into the simulation tab. Once you're here, you're going to want to press TV, highlight this TV, your test bench, and then double click Simulate Behavioral Model. Once you do this, your simulation should start. So now here I have my simulation. In order to see it better, I'm going to change all of these into unsigned decimal. So the code we're going to trace is here. So I'm going to put this next to our simulation. Now, let's look at our code. The first thing we do is an add instruction. So what we're doing is add 10, 15. So what we first need to do is read this instruction. So by default, when the module starts, the program counter starts at 0. You can see the program counter here. So as you can see, it starts with 0. So let's go to the time where reset has ended and we have started our program. So the reset signal has ended here. So we're going to start processing here in the first positive edge. So in the first clock cycle, we're going to read our address, rather our instruction in the 0th address. So as you can see, the address to RAM is right now 0. So in the next clock cycle, we will have this in our data. Here in our data from RAM, you can see this number. This number might not make a lot of sense right now. That is because it is our instruction word. If we were to separate it into components, you will see that it would represent this. So once we have this instruction, what should we do? The first thing we should do is read the value inside A, which is 10 right now. So as you can see, 10 was written into the address. And then, once we have that, which as you can see from the data, it has returned 0. Here, let's look at 10. The value of 10 is 0. So, once we have the value of A, we have to read the value of B, so 15. So let's look. We wrote 15 into the address. So in the next clock cycle, we should get the value of 15. So let's look at the data from RAM. Here we see 2, which is the value of 15. So once we have these, what do? We get 0 and 2, the values we've found, we add them, and then we write them back into the 10th address. So our address is set to 10 again, our data is set to 2, and write enable is enabled. Once we do this, the value 2 will be written into the 10th address. So next up, we have this instruction. So here it says 1 in the address. Why is that? Because we want to read the first address where our next instruction is stored. And before I forget to mention, you can see that the program counter has incremented here. So that is actually what we're writing into the address. So once we do that, we're going to receive the instruction in the next clock cycle. So let's look at data from RAM. Here we have received the instruction. So we've determined that it is an add I instruction. So what we're going to do is first we're going to read the value of A, which is again 10. So we write 10 into the address. Once we do that, we're going to receive data from RAM. Once we do that, we're going to receive the value of 10 in the next clock cycle right here, which is 2. Right, so now we have the value of 10, which is 2, and then we're going to add 20 into it. Not the value of 20, but just 20. So what we do is add 2 to 20, which is 22. We write that data to RAM, enable, write enable, and once that's done, in the next clock cycle, that will be written into our memory. So this is done now. So what we're going to do now is go to our next instruction. So in order to read our next instruction, we're going to write the address that we're going to write the PC into our address. So our PC now has become 2, and we write that value into our address. So we wrote 2. So in the next clock cycle, we're going to receive the instruction that is PZJ35. So that instruction is right here. So once we read that instruction, what we're going to do is we're going to get the value of A once again. So we write 3, which is A, into our address. And then in the next clock cycle, we will receive the value of A, which is 7. So what else do we need to do? We need to get the value of 5 and see if that is equal to 0. So we write 5 into the address, and then we receive a 0. So since 0 is equal to 0, we're going to jump now. Where are we going to jump? we are going to jump into the value of A. So as you can see, the value of A was what? The value of A, which is 3, is equal to 7. So our program counter should be equal to 7 now. As you can see, the program counter went from 2 to 7. So now we're in the 7th instruction. So to read the 7th instruction, we're going to write that into our address. And then here, you can see that we've read our instruction right here. And then what is that instruction? It is another BZJ instruction. So once again, what are we going to do? We're going to read the value of A, which is 3. We write 3 into the address. We receive the value 7. And then we're going to read the value of B, 10. We write 10 into our address. What do we receive? Receive 22. Now, we need to check the value of B, if the value of B is equal to 0. So the value of B is 22, and it is not equal to 0. That means that we are not going to jump, but instead we're going to go to the next instruction. So our program counter is going to increment by 1. So here you can see that our program counter is 7. We're going to increase it by 1, and then which is 8. And once we come to the 8th instruction, what we do is look into the value inside 9, which is 8, and add 0 to it, which is again 8. So it's going to jump into itself. As you can see here, the program counter doesn't change and the program ends here. So that concludes our simulation. If you have done this correctly, you should see total errors is equal to 0 and simulation successfully completed. If you have errors, we are going to receive error messages about it, telling you the time and which instruction you've done incorrectly. And then it's going to say your simulation has failed. So if you receive these 2 comments on your log in your console, your assignment has been completed.